So Kramer's rule is for systems of equations what the quadratic formula is for the quadratic equation. It's a mechanical way to calculate the answer. So same thing for systems of equations with Kramer's rule. Except before we learn Kramer's rule, we have to learn a couple other things. We have to learn how to calculate determinants. So we'll start with a very basic example. In fact, I'll give you the general example in the 2 by 2 case. So let's let A be the following matrix, a little 2 by 2, A, B, C, and D. So if A is that 2 by 2 matrix, then the determinant of A is going to be the product going down, so A times D, minus the product going up, which is C times B, although we typically write things in alphabetical order, so B times C. Let's practice this with problem number 10. Actually, yeah, I'm in the wrong section. Okay, so problem number 10. Matrix A is -2, 1, 3, -2. So the determinant of A is the product going down minus the product going up. And I'll show you in gory detail, although my suggestion to you really is that you do the product part in your head. So product, I would suggest you write 4 minus, and then worry about the product going up. So the determinant of this matrix is 1. Okay, nothing really terribly exciting about that one. Just a little practice with some of the mechanics here. Let's try another one, which might make us think or at least reach for our calculators, and that's problem number 8. 0.2, 0.4, -0.4, and -0.8. So let's check this one out. So again, we want the product going down. Product going down is going to be 0.2 times -0.8 minus the product going up, -0.4 times 0.4. Here are a lot of buttons being pushed on your calculators. So it's going to be a negative. 2 times 8 is 16, and there's 2 decimal places, so -0.16. A minus and a minus is going to be a plus. So what are you getting for this determinant? 0. Now that's going to become important later. In fact, its importance lies in the fact that when this determinant is 0, you can't find the inverse of that matrix. There's no inverse matrix when the determinant is 0. So it's said not to be invertible. We'll discuss more of that later. What we want to build up to is calculating the determinant in the 3 by 3 case. So let's take a look at problems like number 50. Now I'm going to do the 3 by 3 case by example. I'm not necessarily going to be trying to write out, actually, you know what, it's not quite going to be problem number 50. We'll get to the application for problem number 50 in a minute. But for starters, let's calculate, so scratch it, it's not 50. Bless you. Come on. There we go. Let's calculate the determinant of this matrix. It's going to be a 3 by 3 matrix. -2, 0, 1. 1, 2, -1, 3, 5, and 2. Now this is a 3 by 3 matrix, so we're going to have to do something a little bit different in calculating this determinant. I'm going to explain it one way. I think I'll share with you a couple tricks about determinants, but for the most part, I'm going to suggest that we do it more or less one way. So the way I would typically do this, like in a Math 1150 class, is I go across the top row. And you go across the top row, and one at a time, multiply each of these terms by what's called the minor or cofactor. We're going to start by taking -2 times the determinant that would be left if I crossed off the top row and the first column. So if I cross off the top row and the first column, I'm left with a little 2 by 2 matrix. So it's going to be 2, -1, 5, and 2. Now let's continue going across the top. I'm going to have 0 times another determinant. And now I get that determinant by crossing off the top row and the middle column. Now I'll write that just for illustration purposes, but does it really matter what I have here? It doesn't. Why not? Yeah, it's just going to get multiplied by 0. So we'll talk about that in a second. Let's keep going with the last one. Let's follow this pattern. Each time we're going across you cross off the corresponding first row and column. So I'll have 1 times... Tyler, what's that last one I'm going to multiply here by? Thank you. There's one little thing that I haven't figured out yet, or haven't talked about yet, and that's how do I combine these? And the thing is, when you're doing this cofactor expansion, you add these things up with this kind of a pattern, plus, minus, plus. Now, you don't have to limit yourself to just expanding on this row or this column or whatever. You can go anywhere. But this plus, minus, plus pattern holds throughout the matrix. So whatever row or column you expand on, you're going to use these pluses and minuses to help add them up. This is the setup. If you can get here, we can finish it off because we know how to calculate 2 by 2 determinants. So let me pause for a second. Make sure you're comfortable with where we got all this stuff here. Okay, so it's going to be -2 times 4 minus -5 minus 0 times, who cares? Doesn't matter, right? Plus 1 times 5 minus 6. Okay, so that's going to be -2 times 9 minus 0 plus -1. I think that's -19 there for that first determinant. So that's a 3 by 3 determinant. How are you doing on that first one? We okay there? Let's try another one. Give you another example of that. Again, I'm going to give you my own examples. So for the next one, we'll try 2, 0, 1. 9 to -1, and 22, 5, and 2. Now, as I mentioned earlier, you can do that kind of expansion on any row or any column. So let me just pick, for variety's sake, the middle column to expand on. Because it doesn't matter what row or column I choose. So if I expand here, it's going to be, again, 0 times some matrix. Let's put it in there for sake of completeness, just to practice getting those things. So Matt, what number should I put into this matrix, please? Perfect. Thank you, sir. And then I'll continue to go down. Lucas. 2, and then what elements in here?
5, 2, -1, and 1.
Well, you're going to cross off this row and this column.
Then 2, 1, 22, and 2.
Good. 2, 1, 22, and 2. And last but not least, 5 and Olivia. What would I put in corresponding to crossing off this row and this column? 2, 1, 9, -1. Excellent. Now the pattern, in terms of how I add this up, still starts out kind of the same. This is a plus, that's a minus, that's a plus, that's a minus. So in terms of adding these things up, it's minus, plus, and minus. So you see how those alternate. Now your strategy, if you're stuck doing this by hand, is to try and look for a row or column that has as many zeros as possible. And that's good. If you find one, then great. Yes, sir?
So it doesn't matter which column or row you use?
Correct. You want to choose what you find the most easy. Now, I could have expanded across this bottom row, but the downside about that is I miss out on the 0 times who cares. Right? I'd actually have to do some work there. So that'd be a bummer. Cooper? Okay. In order to calculate the determinant, I should probably put DET out here. In order to calculate the determinant of this matrix, I need to come up with all these cofactors, and I need to add them up in the correct way. Now, the correct way to add them up is with, adjusting these cofactors with this sign. I think I might be getting cofactors and minors mixed up, but it's not going to hurt you guys. We need to put in these signs into this equation when I add them up. So it starts out here with a plus, and then it alternates the rest of the way through the matrix. So plus, minus, plus, plus, minus, plus. So any row or column that I expand on, I have to adjust these things using those signs. Okay, yeah. So it starts with a positive and then it alternates throughout. So let's see, we get 2 times, or 0 times that, so it's going to be 0. 4 minus 22 minus 5 times -2 minus 9. So let's see, 2 times -18 minus 5 times -11, 36, 55, 19. Jeff, you're my go-to guy. You already calculated that one?
No, I did it a different way and got a drastically different answer.
Drastically different answer. I'm thinking 19 looks good. Let's see. Let's double check. Okay. All right, so we're good on 19 there. Do you want to practice one more by hand or not? It's up to you. I mean, I'm not the one that's got to be doing this next week on an exam. So, John, you want one more? Okay. All right. Thank you. So let me give you one last one here. So -2, 2, and 1. 1, 9, -1. 3, 22, and 2. And if I want to calculate the determinant of that, well, unfortunately, there's no zeros on any row or column. So it's kind of up to you. Do you have a favorite row or column, the one that looks easiest to expand on? Top row? All right, let's go with the top row then. Top row. So we'll do plus, minus, and plus there. And see what you can do. I'll kind of walk around, help out. Okay. I'll ask you what you get. I'll be impressed when you do it. Okay, so let's see. Plus, minus, plus. So it'd be plus, that's good. It should be a minus there, right? Because you do plus, minus, plus back. Oh, alright. As long as you know what's going on. We'll find out when you get you right the final answer here. Okay. So, I'm sure which one to copy down. You just copy down something.
What is it?
Well, it's this one right here. -2 to 1. And then 1, 9, -9. Or 1, 9, -1, etc.
Here, it's this.
I got something a little bit different. I'm impressed. I'm really impressed. Let's go. Yeah. He's a savant. So yeah. Comes from looking at too much pastry. Okay, so let's take a look at this one. If we cross off the first row and the first column, then we're left with 9, -1, 22, and 2. Cross off the top row and the middle column, we're left with 1, -1, 3, and 2. And finally, first row, third column leaves us with 1, 9, 3, and 22. Now the signs that we adjust with are plus, which doesn't affect this, minus, and a plus. Let's run through the rest of the calculation then. I think we're okay up to here. So it's -2 times 18 minus -22, minus 2 times 2 minus -3, plus 1 times 22 minus 27. So we'll be left with -2 times 40 minus 2 times 5 plus 1 times -5 gives you -95. Whew! Yay! All right, so a fair amount of work to calculate a determinant. But it's a nice thing to know when these determinants are something other than 0, because that means you can find the inverse of that matrix. So you could solve a system of equations using an inverse matrix. Mostly I like Kramer's rule for the fact that it introduces determinants and it shows a connection between determinants and the solutions to systems of equations. Let's discuss Kramer's rule in the 2x2 case. And I think I'll just write it out. Kramer's rule, 2x2 case. So like I said, it's a mechanical way to solve a system of equations. And let's show it in the 2x2 case. Ax plus by equals c. Dx plus ey equals f. So for this generic 2x2 system of equations, what's the solution? Well, we're going to calculate 3 2x2 determinants. We're going to calculate D is the determinant of the matrix of coefficients, so A, B, D, and E. And then I got to calculate 2 more determinants. I'll call one of them dx and the other one dy. And what you should try and pick up here is kind of the pattern of how I generate these things, because I'm not going to try and write this out in the 3x3 case. It's written out for you in the book. It's kind of laborious. So just try and pick up the pattern rather than memorize it outright. To find dx, I'm going to replace the column of x's by the column on the right-hand side. So instead of A and D, I'm going to write C and F. Now the rest of the matrix stays the same. So C and F here, and B and E here. Let's see if we can't repeat that and figure out what dy is going to be like. So for dy, I'm going to kind of do likewise. I'm going to replace the column of y's, that is the coefficients of y here, with C and F. What do you think is going to be left over here? A and D. Oops. A and D. Now that in and of itself is not your solution. There's still one last little step here. And that is x equals dx over d and y equals dy over d. So to actually get x and y, we need to go a little bit further. So it's all mechanical. It's mostly plug and chug. I mean, there's obviously a little bit of thought that goes into it in terms of calculating some of these numbers, but it's a lot of plug and chug. Let's practice with an example. And let's do one that maybe we wouldn't want to do by hand. All right, and that'd be problem number 46. So 10x minus 17, y equals 21. (20x minus 31y equals 30). Okay, well, I would not want to solve this one by substitution. Even the addition method looks kind of, well, the addition method wouldn't be too bad. You can multiply this by -2 and then knock that out. But let's solve it using Cramer's rule. For Cramer's rule, we need a couple determinants. I'm going to start it with the matrix of coefficients. So that's going to be 10, -17, 20, and -31.
It's actually 39.
Is it 39? Did I copy it wrong? Oh, 39 on the right-hand side. All right, 39 here. Whew, cool. So I haven't, all right, good. Thanks, Keating. Let's work on dx. So just in time on that, right? Because we're going to need that 39 right here. So for the next part here, you're going to replace the coefficients of x with that column on the right-hand side. Anyone want to tell me what this one's going to look like? Perfect. So 21 and 39, and then -17 and -31. Nice. Someone else for dy. Paige, what's dy going to look like, please? Good. 21 and 39. So again, see that pattern that after you get d, one at a time to get these other determinants, this column from the right-hand side kind of works its way through. First you get dx, then you get dy by replacing these respective columns. Now, there's some work to do here, right? All right, so let's divvy it up. Thank you. So, Victoria, maybe you can calculate d. Kenny, thanks for volunteering. You can calculate dx. And, let's see. Who have I picked on yet this morning? Yeah, Rebecca. dy. All right. Oh, she's like, oh, got this. All right. 10 times -31 minus 20 times -17. So -310 plus 340. 30? Yes. Oh. Victoria, did you get 30? Say yes. All right, good deal. Kenny, how are we looking on dx? Mm-hmm. Good. What's that turn out to? Yep, that's what I got. And Rebecca.
10 times 39 minus 20 times 21 is -30.
Excellent. Let's put this together and get our solutions. Are we okay with the determinants and the setup of Cramer's rule here in the 2x2 case? I'm thinking I'm only going to do one 2x2 case before we jump into the 3x3 case. I'm not spending a whole lot of time on Cramer's rule. So for the solution, it's going to be dx over d, which is going to be 12 over 30. And let's put that in lowest terms. Yeah, 2/5. And then negative 30 over 30 is negative 1. So 2/5 and negative 1 is our solution there. So a mechanical approach. One thing that might catch your attention if you started thinking about this critically is what's going to happen if the determinant is 0? What's Kramer's rule going to say if the determinant is 0? Yeah, you're going to have problems if the determinant is 0. So if you remember, there's 3 things that can happen when you're solving a system of equations, a 2 by 2 case. You get one solution, the 2 lines cross. You can have 2 parallel lines, in which case there's no solution, or 1 line right on top of the other, in which case there's an infinite number of solutions. Now, it's not something that I'd really want you to try and investigate with Kramer's rule, but you could if d equals 0 and dx and dy equals 0, then the system is dependent. In other words, you have 2 lines, one right on top of the other. If d equals 0 and one of, or at least one, of dx and dy is different than 0, then the system is inconsistent. No solution. I mean, once you find that the determinant is 0, I'm not sure I would proceed all the way through and investigate the rest of this by Kramer's rule. It seems to me pretty inefficient. So it's up to you. But I'm just giving you a heads up. The important thing you should notice is that when d is 0, you're going to have problems. And that's an important thing to know when you're working with a system of equations. Anything else on problem number 46 before we move to 3 by 3 case of Kramer's rule? All right, I'm not going to write down for you the 3 by 3 case in terms of Kramer's rule. We will kind of do it by demonstration, and we'll do that with respect to problem number 50. Okay, so problem number 50 is this. Negative 2a plus c equals 2. You know what? I want to give myself a little more room here because it's not convenient to have the book over here. It's all right. Don't worry about it. A plus 2b minus c equals 9. And 3a plus 5b plus 2c equals 22. Let's go through the setup for Kramer's rule. So for the first thing we're going to need d. D is going to be the determinant of your matrix of coefficients. Patrick, what should I put in for D here?
-2, 0, 1.
Mm-hmm.
1, 2, -1.
Good.
3, 5, and 2.
Perfect. Thank you, sir. Let's keep going. Now, one at a time, we're going to replace these columns by the coefficients on the right-hand side. So by these numbers here, 2, 9, and 22 to get our result, our subsequent matrices, or subsequent determinants. So I'll call the next one D sub A. I'd use an X, except, we've got A, B, and C here. So I'll call it D sub A. Now I'm going to change out the first column, but the next two are going to stay the same. So 0, 2, and 5, 1, -1, and 2. Cool. And then I'm going to want, gotta like this one, DB, and DC. All right, somebody caught that. All right, so for this second one here, or this third one, I'm going to use the first column and the third column. And again, I need to fill in the middle column. So this is going to start looking like this. 2, 9, and 22. 2, 9, and 22. I'll leave it up to you to do the last one. So try and make sure you can write down that last one. What's going to go in that last one? Yes, thank you. So I'm going to write it by columns. So -2, 1, 3, 0, 2, 5, and the last one, 2, 9, and 22. Okay, so I need some answers here. What's D equal? Anyone? Yeah, -19. Good. How about DA? 19. Does anyone recognize this one? You just did it. In fact, we've done all three of these. The three examples we did for 3x3 determinants were each of these. -95. So that leaves us with one 3x3 determinant to calculate. I don't know about you, but I've had enough of doing these by hand.
0.
Is it time to employ some technology? No? Do it by hand? I like living in this stone age. Pull out. Here we go. Wait a minute, wait. We'll pull out the abacus. Yay, do it with that. All right, so I'll pass this around, and each takes turns. I'll come back around 11:30, all right? Let's do these on a calculator. Now, I'll give you a heads up. There's a good chance, some of this stuff I'm going to ask you to do it by hand and show me that you can do it by hand once. But I embrace technology a lot. So where do you think we're going to have to go in order to at least start this calculation of the determinant? Matrix. So hit the second key, then the matrix key, which is above the X inverse key, right there. Let's go over to edit. We want a 3x3, and we'll type in these numbers. -2, 0, 2, 1, 2, 9, 3, 5, 22. And isn't that special? I've already got them here. When you're done entering those into your matrix, then exit, because we're going to need to calculate the determinant. So hit the second key, then the matrix key again. This time we're going to go to a different place. we're going to go over to the math menu. Does there look like there's anything promising here? DET. I probably can't just hit DET and then enter again, right? I need to tell it what I'm taking the determinant of. So go back and press second and then matrix. This time either type the number 1 or press the enter key. Either one will put the determinant of A in there. And I think we had a prediction that the determinant of A was 0, and you are right, sir. So 0. We're not done solving this problem yet, are we? No, but we're really, really close. So we get A is dA over D. So it would be 19 over negative 19. Gives us negative 1. Likewise, B is going to be, negative 95 divided by negative 19, which is going to be 5. And finally, C is going to be 0 over negative 19, which is still 0. The way you'll see your answer written in the back of the book is in this form. It's going to write it in terms of A, B, and C in alphabetical order. Negative 1, 5, and 0. Yay. Can anyone see a drawback to Kramer's rule in this 3x3 case? I mean, it's a mechanical procedure, so in a sense it is kind of plug and chug, but what's a drawback? Oh my God, it's awful. It's a beast. I mean, look, you had to calculate 4 3x3 determinants, and then you still have to do some work beyond that. It's a beast. It's a lot of work. So when I ask this question on an exam, typically what I'll do is I'll give you, say, D, dA, and dC. I'll give you those values. I'll give you 3 of them, and I'll say, okay, set up this last determinant that you would use to solve by Kramer's rule, and then finish solving using Kramer's rule. So I'm not going to tell you which one of these you'll have to work with ahead of time. You have to know how to set them up. But when I ask a question on a test like this, I don't want to see 4 3x3 determinants. It's enough to see it once. So that's what I'll do. So I'll just ask you to calculate one of those, and the rest is up to you to finish this up. Am I clear about what I expect in terms of Kramer's rule? Do you want one more practice problem? Yes? No? Really? Man. All right. Well, we're just going to do the setup, okay? Problem number 52. Two x minus y equals 5. 5x plus 3z equals 19, and 4x plus 7z is 17. So let's just practice the setup part. We're going to start by needing the determinant of some matrices, starting out with the determinant of the matrix of coefficients. For y, thank you. It's just for y. So that first one's going to be 2, negative 1, 0, 5, 0, 3, 0, 4, and 7. And I'm going to need dx, dy, and finally dz. So see if you can't fill in those determinants. Okay. Kenny, why don't you start us out with dx? What's going to go in dx? Wait, back up. Oh, okay, you're going across. All right, 5, -1, 0. All right, that's good. Keep going. Good. Let's keep going with dy. Now, what I did to start this is I just took this column from the right-hand side and I repeated it in different places for dx, dy, and dz. So, first column, second column, third column. And then I'm just going to fill in the rest of this, what remains, with what I have over here. So for this, for dy, it's going to be 2, 5, and 0, and then 0, 3, and 7, and 2, 5, and 0, -1, 0, and 4. For comparison's sake, one of the methods we did earlier this semester in solving 3x3 systems of equations called Gaussian elimination. When you implement it on a computer, they count how many adds, subtracts, and multiplies that you do. And you could solve a 10x10 system of equations with about 340 or so what are called floating point operations, the adds, subtracts, and multiplies. In contrast, if you were to do Kramer's rule for a 10x10, it would take about 3 million floating point operations. It is beastly slow. It's just terrible. I don't know. Because of my background in college, I have real issues with it. It's good in as much as it introduces determinants and it shows you a connection between systems of equations and determinants. But beyond that, not so much. Kenny, does that help? No. I said, well, then it's just some more if it didn't help. No, does this help with your understanding of Kramer's rule? Are you feeling more comfortable? Okay, good. Sure. Anything else on 10.6 here? For homework, try 5 through 13, 21 through 25, 29 through 33, I suggest you do those on the graphing calculator. You can skip 31, and then 43 through 49. So again, I'm really trying to keep the homework to the minimum that I think you need in order to practice. That's section 10.6.